How do you guys go with the assignment project? Okay. Haven't started. Quick start. Start quick. Have you looked at it yet? Not yet? I mean, you should look at it first. Yeah. Think about it. Huh? I mean, just read the sentence first. Yeah. I mean, yeah, don't keep everything to the last. Okay. Start thinking about it. I think you still got a habit that when you start, you need to finish it. Finish at a short time or what? Because sometimes the question is really hard. You can't do it like that. Because sometimes the idea need to sink in. So try and read first, and then you can do other stuff first, and then come back. Okay. Don't just spend the whole day thinking about it. Okay. Yeah. How about projects? I think few of you already sent me your draft already, and then for those who haven't decided, please send me by this weekend. Okay. Decide what you need to do. So next Wednesday, you need to turn in your assignment, is it? Yeah, and then the following Wednesday, we have our presentation. And then Thursday is project and presentation. And so next Wednesday, right? I mean, for the 28th, I was thinking that maybe we will start at 1 o'clock in this class. I think 1 o'clock, this class is free. So if we start earlier, we finish earlier, then we finish earlier. Otherwise, maybe I scared it will drag times. Okay. So we'll try and end at 5 or before 5. If not, maybe it will be after 5, a little bit after 5. I hope not. Okay. I'll make announcement. So 28th, we start at 1 o'clock. So if we end earlier, then we finish earlier. If not, we will try and finish before 5. Okay. And I invited some of the students from the other class. Some of them maybe were present. Yeah. I think some of them are your friends of some of you. Yeah. And you can invite your friends to come also. But let me know beforehand so that we have enough space for them. And you also can invite your lecturer to come if you want. Any question? Any question about lectures or assignment projects? Or start. So I constantly update the lecture notes again. So please download the latest file to read. And if you found anything not right, just let me know. All right. I was still marking your project one, so please be patient. I'll release them once I finish. And for project one, right, after I release, you can make correction. If you make correction, I can give you extra mark up to 2 marks. Okay, of course you won't get more than 10 marks, but yeah, this is the idea. Okay, if after I mark, I return to you, you make correction, you hand it back to me, and then I'll give you extra 2 marks, up to maximum 2 marks. Okay, and I will release all the projects to the class, and then every one of you can read each other's works. Okay. Yeah. Okay. So we're closing up the chapter multiple integral. For this hour, maybe we'll try and do some more exercise to run through the concept. So let's spend some time reading this question here. So we have a multiple integral here, okay, on a function, two variable function but triple integral. And this region here is bounded by a paraboloid and a plane. Okay, so where does this graph lies? What space does this graph lies? Huh? R3? You sure? The domain is R3, the codomain is R. So where does this graph lies? R4. Okay, so we can't quite draw the R4 out. Okay, we can't quite draw the graph out, but we can draw the domain. Okay, the domain is in R3. So we have this paraboloid. Okay, I just realized that you guys learned conic section in your previous year course, maybe previous semester course, is it? Okay, so you should recall the conic section knowledge to help you. Okay, so y equals to x squared plus z squared is a paraboloid. And evaluate the multiple integral over this region here. All right. So what should we do? Any idea on how to do this triple integral here? Does any variable that you know how to bound it, given this information here? Do you know how to bound any of the variable x, y, or z? So that square root equals to uh, square root y minus x squared. Do you mean this? Negative. Then let's say equal to square root y minus x squared. All right, sure. Okay. How about your x and y? How about your y, x? Let's do the 2. Okay. Oh, all right. You get this. So how do you read this? How do you get this? Okay. So maybe we can see from this x here, is it? So let's fix what is x. Okay. So x is going from -2 to 2. Is that right? Okay. So let's check what happened to this domain here. So we cut this parabola at y equals to 4. So y equals to 4, meaning x squared plus z squared equals to 4. Okay? X squared plus z squared equals to 4 is what? Is a circle. Okay, circle center at the origin with radius 2. But this circle lives in the plane of xz plane. Okay, so it's on the xz plane. So let me draw it out. Z plane. Okay, so if it is a center at xz plane, the interval for x is going from -2 to 2 because it's radius 2, right, from the origin. All right. How about y? How you determine y? So you fix an x, right? You fix an x. You need to know how this y grow, right? How the y grow. You fix an x, you need to know how the y is grown. So how do you see this? X squared less than y less than 4. How do you see this? How do you see this? So you fix an x, right? Okay, you fix an x. You need to see how the y grows. Okay, in this case here, if you're fixing x, what do you mean by fixing x? Are you looking at a line or a plane of x? You fix x in 3-dimensional. Okay, what does x equals to 2 in 3-dimensional means? Is a line or a plane? Huh? Is a plane. Okay, so this x equals to is a plane in R3. Okay, so meaning you need to look at the intersection between a plane and a paraboloid. Make sense? Make sense or not? Does it make sense? Does it make sense? Okay. 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 So so you look at the uh, plane in R3. Sorry. Okay. Yeah. So what are you finding here? So you fix an x, you try and find what is y. So how do you produce this picture here? How do you produce the picture for y? You produce picture for y. Idea. Hmm. Hmm. Idea. Is equals to power 4. Any idea how to obtain this second inequality here? Okay. Huh? What are you trying to say? So 您 say what to me? We are just trying to verify this. Yeah, we are trying to verify is this true or not. Yeah, we're trying to verify whether it's true or not. So I mean, okay, from here, okay, we know that x is between -2 and 2. So how we decide y? Maybe y is in between x squared. I mean, okay. So I mean, how do you see this? How do you see this picture? How about x squared and equal 4? Okay, so I mean, let me, how should I draw it? Uh, Draw the parabola, right? Okay. So let me see how should I draw it. How should I make it? So maybe I draw like this. Okay. And then my Z is in this way. My okay. Okay. So if I look at x equals to 2 and x equals to minus 2, what is my y? What is my y? My y is just 1 point at the end point. Okay? And then what happen if I go into x in between minus 2 and 2? What happened? Where's my y? Huh? Where's my y? Okay, so meaning what? Uh meaning meaning we need to. Okay, so let's look at just one slice. Look at z equals to 0 slice. Okay, when z equals 0, what happened? At the slice of z equals 0, what do you get? You get y equals to x squared. Okay, so meaning, okay, so how you should imagine this here? Okay, so you should imagine we take the 0 slice here. Can I draw the 0 slice well? And this, can you see what I'm trying to draw it here? So let me redraw this. Yeah, you mean this? Should be x squared, is it? Yeah, yeah, yeah. We are trying to verify this. We are trying to verify this. Yeah, this is okay, okay, okay. Let me write here. So this one is suggestion. So let's try and verify this. Okay. So let's take the slice. Let's take the slice of um, let's take this slice here. Let's take this slice here. Okay, let's take this slice here. Is it clear what am I doing here? Is it clear now? I take the z equals 0 slice of my parabola. Okay, and then I see what happened to my y. Is it okay? Okay. Why? Do you know what I'm doing? Are you getting what I'm doing now? Trying to get. Okay, what I'm doing is I take the z equals 0 slice of this parabola. Okay, so meaning I cut it here. I mean, I chop it. Okay, and then I look at this graph here. What's this graph? This is y equals to x squared. Y equals x squared. Okay, so for every x in between here, what happened to my y? My y is bounded below by x squared and bounded above by x equal to 4. So this point here is x equal to 4. So maybe use another color. X equal to 4. Is it okay? Okay. Okay. So, but this is not enough, right? This is just a single slice of my parabola. Okay. What I need to do is I add up all the slices along the z. Okay. So what are the z I need to consider here? What are the z I need to consider here? What are the z I need to consider here? Yeah, the two semicircle given by the z. Okay, so let me draw it. Yeah, so the two semicircle given by the z direction. Okay, so okay, so there are a few things going on here. Okay, so let me draw this along z direction first. So you see, this is a z direction. Okay, let me draw a big cylinder. This is the z direction. Okay, this is the z correct. This is z direction, and then okay, and then what we do is we attach this what's this direction? Okay, so to be precise, let me think how should I put it. Okay, to say better, let me say that this is in let me write. This is in ZY plane. Okay, so you imagine this is a ZY plane. Okay, you got a parabola. Okay, and then you got for each Z. Okay, you also have a parabola at what's this plane? XY plane. XY plane. So this is XY plane. Okay, so you should think of this ZY as a skeleton. Okay, above this skeleton, you put an orthogonal parabola. Can you think of this picture here? So let me draw it more rigidly. So along this skeleton, okay, let me put dotted line when we go backward. Okay, along this skeleton, I put parabola. Imagine this. Um, okay, so maybe can someone help me? Someone help me. Help me hold this cable here. Someone help me hold this cable here. Yeah. So okay. So you should imagine this as a ZY plane. Okay, this is a ZY plane. Okay. You come to this side. Yeah. Okay. And then you have this along XY plane, you have this yellow. And another one, help me hold this this side. Hey. Okay. Can you go can you stand here? Okay. So you see. So this is the so imagine this white line as a red line there. Okay. Along this white line, you have this yellow line. Okay. Can you move along with me? Yeah. So you move like this. Okay. So all together, you will form this parabola. Can you imagine or not? Okay. So first what you do? First, along x, okay, along x, you have this change of y, okay, and then you have all these line along the z direction. Okay or not? Is it okay? Okay. Okay. So just now, why you talk about this negative square root and positive square root, right? This represent the two half of my parabola on the zy plane. Yeah, thank you. Thank you, Sui and Wensuo. Can everyone imagine that? Yeah. Okay. So one way you can do this is using what Suoning said. So you just integrate this from -2 to integrate from x squared to 4, and then square root y minus x squared to square root y minus x squared of the function. So it is dx, dz, dy, and dx. Okay. Actually, I think there's another easier way to say it. Okay, there's an easier way. Okay. What's the easier way? Instead of bounding x first, okay, I will bound my y. I will bound my y last instead of z. Okay. So what I do is I'll bound my y. Sorry, I'll bound so second. Here. Okay, what I do is I bound my y first. Okay. You can see that my y will stop at 4. Okay. And then it is bounded by x squared plus z squared. Okay. So I'll bound my y. I'll bound my y using 4 and x squared plus z squared. Okay. Then next I need to decide how I bound my x and y. Okay. How do I bound my x and y? X and z. Okay. You can see that x and z here, right? Okay, is given by this parabola here. Okay. So everything within the circle, I need it. Okay. Everything within the circle, I need it. And how about my radius? Okay, my radius is only going from 0 to 2. So meaning what? Okay, so let me show you something. So first of all, the integral here can be split into the height. Okay, plus something two-dimensional. Okay, so what's this two-dimensional? You already get away the height. Okay, you get rid of the height. What else do you left? What else do you left? You get away with the height. What else do you have? You get away of the height of your parabola, then what else do you get? What you get is just this circle here. Okay. Does it make sense or not? So everything that satisfies that needs to consider is this xz is the xz inside the circle of radius 2. Okay. So all the xz is in D. All the xz, let me write. So okay, all the xz, how should I write it? All the xz, okay, all the x, y, z in D must satisfy, sorry, all the x, y, z in E must satisfy xz in D. So what's D here? D is the circle. Sorry, this is that. So these are the circle x squared plus z squared equals to 4. Okay. Does it make sense or not? Because why? Because for every so let me write it out. Not equal to 4, but all the things that's less than equal to 4. Okay. Why? Just now we already deduced that all the xz here must satisfy this y. Okay. And then this y here is what? Is going between 4 and x. Okay. All the y here is go between 4 and x. But x can be 0 also, because we are considering x in between 2 and minus 2. Make sense or not? Does it make sense? Make sense? Doesn't make sense. Following or not? Does anyone know why, if my point in E, okay, the xz coordinate must satisfy the equation of square, equation of circle? follow. Qifeng, do you know why? Don't know. Okay. Don't know, that's fine. Okay. Okay. So if you fix the y, okay, so let's see from this paraboloid equation here. If you fix the y, what do you get? A circle equation. Okay, you got a circle equation here. So how many y you need to consider? What are the y you need to consider? You are considering all the y from 4 to 0. Make sense or not? Okay, so in this case here, all the circle with radius between 0 and 4 you consider. Okay, all the exact need to satisfy this circle equation. Meaning what? Meaning the exact lies inside the disk of radius 4. Make sense or not? So, okay, so the idea you need to keep in your mind is this is an infinitely many circle here. Okay, and then we got all the radius of the circle between 0 and 4. Does it make more sense now? Michelle, do you understand? Okay. Yeah. Okay. Okay. Please give me some feedback. If no feedback, then I think you all confused already. And let me know why you confused also. Question. Why the lower bar is x squared plus x squared? This one here. Okay. So because this here, why lower bar is x squared plus x squared? Because because what we are trying to do here is we are fixing the two-dimensional domain first, and then we fix y last. Okay, and then this y will change with respect to the point in the two-dimensional domain. Make sense or not? Does it make sense? Okay, let's look at this picture here. If I pick any x and z here, can you see? You don't get the whole cylinder. Okay? So if I don't bound below by that function, what I get is a cylinder. If I get the whole thing, if I let's say y is bounded by 4 and 0, okay, and then we have all the circle. Okay, we have all the circle. Okay, what I get is just a cylinder. But how do I get rid of the extra stuff here? This extra stuff is controlled by the paraboloid function. Okay, so it's bounded below by a paraboloid. Okay or not? I mean, if you don't understand something, right, try and play around with this equation here. Okay, so let's say I bounded by 0. What happened? I will get a cylinder. Okay, but this cylinder is not the region I want. Okay, I need to cut off some of the bottom stuff. So what are the stuff I need to cut off? It is exactly cut off by the equation of paraboloid. Jiangchen. Do you get what I say? You get what I say? Okay. Yijing and Yijing. Do you get what I said? Okay. Okay. Yeah. Okay. So what to do here? So what's next? What's next? So why I prefer this over that one? Because for the this we can all automatically make it into a polar rectangle. Okay, so what's the polar rectangle here? So these are just the point that is have wing radius from 0 to 2 and the angle from 0 to 2. Okay. Okay, but if you use the previous one, okay, then you need to do some appropriate change. But what you do, when you change this into polar coordinate, I think this is also what you did, similar to what I do now. You can try it. Yeah. Maybe soon you can try this also. Yeah, I mean turn that into a polar coordinate and then do it. If you want to do it in brute force also can. Maybe you need to use arctangent stuff. Yeah. Question? Which one? Which one? This one? This one? Oh, I think it should be just x squared. I just typo. Just write it wrong. Okay. Okay. So yeah. So if I do this integral here, what will this become? Okay. Because there's no y inside my variable, so I just what do I do? I just uh, I just wrote it as square root x squared plus z squared times 4 minus x squared minus z squared. Okay, dA. Okay, and then we want to integrate this over this. What do? We change this to a polar coordinate. Okay, we change this into a polar coordinate. So how to change it into a polar coordinate? So make it into dr d theta. So remember that there's a Jacobian change here. So we introduce the extra radius. Okay, and then integrate from 0 to 2 pi for the angle, and then 0 to 2 for radius, multiply by the change of variable here. So what does this become? What does this function become? What does this function become? Grace, do you have an idea? No idea. What's the variable change we need to do here? X equals to r cos theta and y equals to r sine theta. Okay, so under this variable change, what happened to this x and z? Okay, x squared plus z squared equals to r squared. Okay, so what happened here? So what do we get? R times 4 minus r squared. Okay, so you do this relatively easier integral. Okay, so these are just integration of polynomial. Okay, does it make sense? Thanks or not? Any question? So when you want to obtain this change of domain, right, you need to imagine how you build the space. Okay, you need to imagine how you build the space, how you slice the space. Okay. Remember last time we talked about the idea how you go from 0-dimensional to 1-dimensional to 2-dimensional. So you need to think about how you slice the space out. Is it okay? Okay. Okay. Question? Mm. Does uh-huh. Uh Depends. Okay, depends. Yeah. Might not be given. Mm. But yeah. Yeah, might not be given. But in this case here, right, this one here, the way the other class learned the conic section. So how to see this as a paraboloid? You need to look at cross section. Okay, you need to fix the constant y. What happened in the y direction? Fix the constant x. What happened in the x direction? What happened in the z direction? Okay. Yeah. So you can see if I fix y, right, I got a bunch of circle. Okay. I fix y, I got a bunch of circle. If I fix z, x, what do I get? I get a bunch of parabola. Fix z direction, also a bunch of parabola. Okay, so how you put this circle and then parabola together? Then in the end, you will get this whole parabola here. Okay, this is amount to how you cut this surface. Okay, you can slice, you can chop the surface this way. You can chop it this way, or chop it in the y direction. You will get a bunch of circle. Okay, make sense or not? Okay, so this depend on how you chop this surface up. You will get parabola in this way, and then in that way, and in this way. Okay, let me show you a picture. I think I have some picture drawn for the other class. Yeah, this one here. See? How do you build a parabola? Okay, you can see there are different slices here. There are orange slice, green slice, and the purple slice. Okay, if you chop at the purple level, you will get a bunch of circle. And then if you chop as a orange side, you will get this parabola. And then you slice at the green side, you will get this going from front to backward. Okay, all these together make up this parabola. Can you imagine or not? Grace, can you imagine? Imagine? Huh? Can repeat again? Yeah, okay. So we're trying to draw something paraboloid. Okay. So there are three ways to cut this paraboloid. Parabola is in 3 dimensions, right? So you just use the XY plane, XZ plane, YZ plane and cut it. Okay. So if you cut it differently, for example, if I cut like this horizontally, okay, using the XY plane, what I get is circle. Bunch of circle. Okay. If I cut in the YZ direction, okay, I get paraboloid going forward to backward, front to back. Okay, paraboloid. And then if I cut it XZ direction, I get the yellow paraboloid, the orange paraboloid. Okay, so you patch these three pictures together, you patch all the paraboloid together using the circle. What you get is this solid cone here. Not solid, I mean just cone. Okay. Okay. So I mean integration domain depend on how you cut the surface out. Yes, yes, because you can cut three ways. 3 dimensional, you can cut three ways. Mm. 3 dimensional, yeah. Mm. I mean, there are different ways to cut it also. You can slant your plane and then cut it. But I mean, these three together enough for you to understand it. Yeah. You can slanted your plane and then cut it also can. But I mean, these three do what? Slender position. Yeah, you can cut it in a slender position like this. So you also get some slanted parabola here. Oh, sure. Unless you change your XYZ into that direction. If not, it's not helpful. Yeah, it's like directional derivative. Unless you change your direction to U, not XYZ anymore. So you differentiate with respect to U. But it's possible. How? We learned this before. This is the change of transition, the transformation. Okay, the transformation of variable. Okay. Any more question or not? Can imagine. So when you do exercises, right, try and imagine how you cut the spaces out. Okay, try and imagine. This will help you to determine what integration domain you need. Any question? No question? We only managed to do one exercise in 1 hour. Huh? Good progress. But make sure in this 1 hour you really understand this example, okay? Otherwise, it's a waste of time. Okay? Make sure in this hour you really understand this example. Okay? And then it's not a waste of time. Why? Because you learn something. As long as you learn something, it's okay. Although it's slow, but you will catch up eventually. Okay. Slow is not frightening. Okay, but don't stand. Okay, don't stand. Slow is not frightening, but don't stand. Don't stand still. Okay. Yeah. So hopefully you can get something. I mean, learning, right? Learning stuff is really depend on your motivation. So you need to find your motivation to learn. Yeah. Otherwise, I cannot help you. Yeah. You need to find your motivation. What else? Okay, so maybe I left some of them as homework. I will provide solution. There are a few more change of variable question. Okay. Then maybe we do one change of transformation. How about we come back at 12? Okay, we'll come back at 12. And then we'll discuss one more example of change of transformation. See how the Jacobian change. Okay? Back.
我这个都不，
嗯
我这个你找一个真实的例子，
哼，有吗？
像我找了，
没有。
对，现在没找到我不好说。
说那种政府啊，他们没有来对他们自己的人民做那些statistic 的那个
这个
统计。
这个统计是有，但是好像这并没有用那个算出积分的方法来算，这个实例找不到。可能就是相关的数据能找，但是这个方法
啊，
好像是没有。
OK， 哦，OK，这样，嗯，因为我不知道你那个方针，你这样子放进来有什么意义，对吧？我可以
就
容易放一个方针进来，是不是？所以那个方针到底在那个实际的生活里到底起有什么意义，我不是很清楚，这是我的点。
就是那个
对啊，一啊，你放那个
FXY
啊，你放那个 epsilon 对吗？
啊。
这样如果我放一个 polynomial 啊，我还是我放一个有什么差吗？对吗？你懂我什么意思吗？就是有一点太随便。
哦，是
啊，
就这个我看了一下，就是现实生活里的这一个 FXY，
嗯哼。
就是非常的复杂，并且这个数值不能确定，有一堆字母需要根据现实情况。
对，所以我就说，你可以说这里就考虑一个最 approximate 的咯。但是就是因为我不知道你那个东西从哪里来，所以如果你现在说的这个东西是有根据吗？
没有，
没有根据。
对，就是
有没有类似他们用的东西？比如说他们可能研究动物啊，应该动物很多呀，不要忘记。应该
哦，
啊
哦，就是要把那个 FXY 弄成一个比较合理的一个。
就是为什么他们会取这个那个方向？虽然说它不是最准确，但是为什么他们会用这个方向来说？
哦，就是需要解释一下这个。
大概的，就是大概说的呀，不然的话就是太随便啊。你放一个一，我也可以放一个任意的东西啊，所以这样子我这样子算出来的东西到底准不准呢？还是到底有什么实际的帮助？还是这样，你明白吗？
嗯。
我觉得应该有人做过吧，你可以看一下什么 joint probability 哦，什么 biology 的东西啊等等。
哦，就是找一个相对更合理的方程，并且稍微解释一下这是怎么来的。
啊啊
哦，
啊，或者他们可能已经取了一大堆的那个数据，然后他们对这个数据看它的方程怎么变化，或者他已经从它数据，因为你从数据那边可以算 probability 嘛，对不对？他们现在只是要找一个方法来形容那个 probability 嘛，是不是这么说？
嗯。
对
好，
对对
我回去试着找一
呀
下。
呀，嗯
这个除了这个，就是
嗯哼，
这个解题的过程，还有其他的地方可以理解。
怎么说？
这个解题的过程，
啊哈，
还有
你说
其他，
哪一个解题过程？
就是我不是试了2问吗？第一问是算概率，第二问是求那个 BMI 的
啊啊啊啊啊
算，
啊哈，
就是就是这2问的过程就是
这两个的过程有什么问题？什么意思啊？
不是，就是我的意思是，就是我发了那个 project，
对
除了那一个
对，
FXY 就是需要改进之外，还有其他地方。
其他应该正常吧？应该正常吧？啊、你的 expected value，你的 definition 就是那样的，对吧？就是 gx 乘以你之前的那个，嗯，是不是叫 distribution 还是叫什么 density function 还是什么之类的
但是的。
呀？啊呀，我觉得那个正常。
就是没有
对，
什么需要。
嗯，但是我觉得你要解释一下 expected value 在日常生活中什么意思？它就是说就是最容易你就是说你测量的时候，你最容易得到的数字就是这个，它的
嗯
平均值是不是这样？因为 expected value 是一个specific 的分嘛，对不对？如果放在现实生活中，它是什么意思？它是不是说它的平均值啊，就是意思说它 expected 它那个 value 嘛，就是说每一次测量就是大部分会遇到这个数字，是不是这么说？近或者在它附近，平均值嘛，是不是这个理解？expected
嗯
value 的理解。
是。
对，你要把它，就是你要把它在现实生活中的 interpretation 写出来。对，现实生活中的 interpretation，因为你放在 human type 嘛，所以 expected value 在算什么东西？到底什么是 expected value 在那个？
哦，
明白吗？
行，我得想一想，不会的话就算了。
啊，可以，你再问我。
呃，就这一个篇幅就是你觉得就是
OK 啊，够长啊，够长。什
啊
么篇幅啊？长不长？长
不
短？
需要再加了。
不用，
啊
就合理化你的东西就可以。
啊，
也不用够长啊，也。因为什么？哦，等一下结束了之后再看一下。OK，那个，又要问吗？Where's 离开啊？Overslept again？啊？Yes 啊？How do you know? Someone tell you? Oh, so he tell you or what? Others? So weird one. Sure. Mm-hmm.
有点不能要转去森林这个，
嗯哼，
不是，就因为我们转这个，我的这个编制完了，
是邻居哥呀。
然后因为他的 Z 是，因为他的 Y 是从编到这边，
嗯哼，
所以你就设为 X square Y 这样再搞，这个是 R square，
你说你要用写邻居哥是不是
嗯，
？OK，等我看一下啊，答案算出来了。
然后算出来怪怪的，
因为你的死邻居哥是不是那个不是？因为我想一下死邻居哥的话是什么情况啊？死邻居哥，哎，我觉得死邻居哥好像可以，可是我看一下啊，你算错东西。
不懂，因为我丢，因为这个是你的嘛，我丢弃一部分的话，它算答案讲的
对，我
话，
看一下这边的答案，
我审一下答案不对。
答案是这个128拍over15，然后是个 SM。
我都不懂去哪里了。哎，错，应该是都没错。八跟其他没有
哦，不对，没问题。
歪了，再歪过是错。
一方程先没有出错。
这是 I 的，对不对？
r square 要除二啊，r cube r square 没有除二呢，不是 r cube 哦，OK，sorry，看错了。哦，对，
嗯，
喂，你看啊，r r4啊，这个是 r to the power 4。
哦
呀，再出来看。OK，yeah，I think yeah，觉得你的答案你做好发给我一下。Okay，yeah，I think means you got a brilliant way just now. I think there's another way to solve this. So this is a cylinder, okay, cylinder, but controlled by this height. Hey, actually, same as mine, isn't it? Means you same as my method. It's same as my method. It's the same. Huh? You wasn't listening. Yeah, the problem with this class is that you guys don't listen to what I say. So like this cannot communicate, you know. If you don't listen to people say, what people say, cannot communicate. Anyway, yeah. Yeah, we need to listen to each other so that we can communicate. Okay. So let's do one more example for this change of variable. Okay. So we have this function here, exponential to the x plus y over x minus y dA. Okay. So what's this graph here? Where does this graph lies? Graph of the function you want to integrate. Lies in where? Huh? Lies in where? R3. Okay, so this is the R3. So you find a double integral of a graph in R3. Okay, so your domain is in R2. So your domain is R2. Okay, so this domain is a trapezoidal region with 4 axes or 4 vertices. Okay, so you plot out 4 vertices here, and then you form the trapezoidal region. Okay, so you can see that this function here, there's few variables stuck together. Okay, so kind of complicated function here. So we can do some change of variable here. Okay, we can do some change of variable to make this equation look better. So we can make change of variable here to make this equation look better. Okay, so what to do here? We can make a change of variable to u and v. Okay, where u is equals to, okay, let me write down. So change of variable. So the transformation. What I can do is I let u equals to x minus y, v equals to x plus y. Okay. So in this case, I also know how to change my x and y from u and v. Okay. Wait, let me see. So maybe I swap it this and then swap it. Okay. U minus VO2. Okay. In this case here, okay, we swap this into a UV integral. Okay, we don't quite know what's the region change here. Okay. But we need to introduce an extra Jacobian here. Okay. Remember how to find this Jacobian? You remember how to find this Jacobian? Does Venus know how to remember how to find the Jacobian? How to set out the Jacobian? Okay, how do you set out the Jacobian? Venus. Okay. Of, yeah, all the partial derivatives. So how do you arrange them? What's the first entry? Del x over del u. Sure. How about second entry in the row? Okay, sure. And then third entry, del y over del u and del y over del v. Okay. Okay. So what's this here? Okay, what is del x over del u? del x over del u here is 1/2. Okay. Del x over del v is 1/2. And del y over del u is also 1/2. And del y over del v is minus half. Okay, so altogether we get minus AB minus DC. Okay, but we are taking the absolute value of our Jacobian, which is half du dv. Okay, so what happened to our integral domain here? What happened to the integration domain here? Okay, let's see what happened to this line. Okay, let's see what happened to this line. So how many lines do we have? We have 4 lines here. Okay, we have 4 lines here. First, we check what happened to the boundary. Okay, first we check what happened to the boundary. So let's check what happened to this. So let's call the name R1, R2, R3, and R4. Okay, what happened to R3? Okay, what happened to R3? So when U equals to V, okay, when U equals to V, what happened? What am I doing here? So sorry, actually we start with the bottom one. So let's move it down, move it down, move it down, move it down. Okay, so we start with X, picture X, XY plane. And then we want to go to UV plane. Okay, we go from XY plane to UV plane. Do you realize that we have different order here? T inverse and T here. This is because of the convention we use in our theorem. Okay, so our theorem is going from TUV to XY. Okay. So UV is the new variable. So these are the new variable. XY are the old variable. Okay. Yeah. Okay. That's why our Jacobian lists it as a UV instead of XY. Okay. This is due to the due to the convention theorem. Okay. Yeah. Okay, so we need to know what happens after we go to the new coordinate. Okay, what happens when we go to the new coordinate? So where does this SR1 map to? R1 is what line here? This is a line of y equals to 0. But our x is taking from 1 to 2. Okay. So what happened to the UV plane? What does this line map to? So you get the equation u equals to x and v equals to x, which means u equals to v. Okay, so you get a line u equals to v. Okay, but from where to where? From where to where? From where to where? Your x is controlled by 1 and 2. So you start with 1, 1 and end with 2, 2. Okay, so that's why you got this line here. Yes. Okay, your u and v is controlled by x, but my x is going from 1 to 2. Okay, so we go from 1, 1 to 2, 2. So which is this u equals to v line here? Following? Following or not? Okay, so when x equals to 1, okay, let's move it down. So x equals to 1, okay. When x equals to 1, u equals to 1, v equals to 1. Okay. And then when x equals to 2, u equals to 2, v equals to 2. Okay. Sometimes, right, you don't care about what I wrote first. Listen to what I say first. Okay, don't care about what happened in the black box. Just listen to what I said. After you know what I said, then you look at the board. Okay, otherwise you will confuse sometimes. Okay, so listen to what I said first. Okay, don't look at the board first. Listen first. Okay, what is R2? Okay, R2 they compute for you already the length. Okay, I mean the equation. If they don't compute for you the equation, do you know how to compute this equation? Given 2 points, do you know how to compute the equation? So you get the gradient and then you find the line of equation. Okay, let's say you compute this line of equation. So what happened to this? You have x minus 2 equals to 2. Okay, on this side here. This meaning what? This give what? What does this give for u and v? In particular, for v is x minus y, which is 2. Okay, your v is always 2. Your v is always 2. Okay, your v is always 2. So your v is always 2, but what's the end point and the starting point? So in this case here, your starting point is from where? From 2, 0 to 0 minus 2. Okay. So what happened to your new starting point? Okay. So when let me put it down. So when xy equals to 2, 0, what happened to uv? Okay, uv in this case here is x plus y and x minus y. So you get 2, 2. Okay, so 2, 0 get mapped to 2, 2. Okay, and then how about 0 minus 2? It get mapped to minus 2 and minus 2. Is it minus 2, minus 2? So minus 2 and one of them is x plus 1. So one of them is x plus 1, x plus y. Okay, the other is x minus y. So let me move it down first. So x plus y, x minus y. So I get minus 2. Okay. Okay, so let's go to this picture here. So this R2 here get mapped to v equals to 2 line. Okay. And then the point 2, 0 get mapped to 2, 2. And then minus 0 minus 2 get mapped to minus 2, 2. Okay. Make sense? Okay. Okay. And then you can do it the same for R3 and R4. Okay. So you do it the same for R3 and R4. Do you want to do it together or you can check? Check together? Check together? Okay. So let's do R3. So what is R3? R3 is y equals 0. Sorry, x equals 0. Okay, x equals 0 from where to where? From y from minus 1 to minus 2 to minus 1. Okay. So when x equals 0, what happened to our u and v? What's our change of variable for u and v? X plus y and x minus y. So in this case here, we get y equals to u and v equals to u. Okay. So this gives what? This gives that u equals to v. Okay, so you get the u equals to v line. Does it make sense? Oh, v is minus y, good. So since v is minus y, instead of u minus v, we get u equals to minus v. Okay, yeah, okay, good. Okay, very good. So what next? How do we end and start the line? Where do we end and start the line? So we start at -2, okay, and end with -1. Okay, so the starting point is in uv. Where's the starting point? When y equals to -2, uv equals to what? -2 and 2. Okay, when y equals to -1, what happened to our uv? It is -1 and 1. Okay, so let's go back to this picture here. So R3 is this part here. Okay, so we just send it to u equals to minus v, starting from -2 to -1, and then this is the u minus v line. Can follow? Okay. 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 So how about R4? Okay, how about R4? How about R4? R4 is what line here? Okay, this is a line x minus y equals to 1. From where to where? From -1, 0. Sorry, from 0, -1 to 1, 0. Okay. So in this case here, u and v, okay, which one is x minus y? V is x minus y. Okay, so this means this v here is fixed by 1. Where this is the v equals to 1 line. Right? Okay. So where does it start at n? Okay, when xy equals to 0, -1. What is our uv? Our uv become -1 and 1. Right? X plus y and x minus y. Okay. When xy equals to 1, 0, what happened to our uv? What happened to our uv? Become 1 and 1. X plus y, x minus y. Okay. So let's put it back to this picture again. Okay. So this is the R4. Okay. 0 minus 1. Okay. 0 minus 1 gets sent to -1, 1. And 1, 0 gets sent to 1, 1. And then the line that connects them is v equals to 1. Okay. Maybe you will ask, what happened to the point inside here? What happened to the point inside here? How to check for the point inside here? Okay. In principle, what you can do is you can look at all these lines. Okay. And then you should see that these lines get mapped to everything inside here. Right. So how to split a surface into lines? There are infinitely many lines. Okay, you check for this infinitely many lines. Is it okay? Is it okay? Yeah. So in sometimes, okay, instead of checking this boundary, right? I think really is better where we can check this all these lines here. So somehow when we check this boundary, right? Actually, we are checking this line. Yeah, in some way, Okay. But in general, right? When we do the map change, maybe we will flip the region inside to outside sometimes. Yeah. Okay. Yeah. But I mean, for this courses, I think we won't do that. Yeah. Trigger. Yeah. But I mean, if you really want to do the check, what you can do is you produce all this infinite line. You can do it, right? You just take the range of the gradient. No, wait, sorry. I'm saying stupid stuff. So the gradient is the same, okay? But the intersection of y is different. Okay, intersection of y is going from -2 to -1. Then you can produce all the line. Make sense or not? Okay. Yeah. So I mean, yeah, you can check all these lines because I already show you how to check for one line, right? You can check for all the lines here. And you can see that these lines are mapped to somewhere in between. For this course. Okay. Yeah. Okay. Yeah. Okay. Yeah, for this course. Okay. Okay, and then after all we found this integration this domain here. So we need to change our integration domain. How do we change this? How do we decide the integration domain here? So we want to if we want to do du dv, okay, we need to set our v range first, correct? So we set the outermost range first, and then we set what happened to my du. Correct or not? Okay. So my v is going from where to where? It's very clear here. We are going from 2 to 1. Right? Okay, we're going from 2 to 1. Okay. So along each v, right? How my u change? How does my u change? So my v is bounded by 2 and -1. Okay. How does my u change? How does my u change? If I integrate along v equals to 2, it is going from -2 to 2. If I integrate along v equals to 1, it is -1 to 1. How about the rest? Huh? Sorry? -3. Oh, minus v to v. Okay. So in the middle, the bound of my v is from -v to v. Okay. Bounded by this. Sure. Good. Okay. So my integration domain for u is -v to v. Okay. Times what? Times e to the u over v divided by 2 du. Sorry. Yeah, du dv. Okay. Yeah. So can you integrate this? So how do we integrate this? Okay, so what we do, we can integrate our exponential function where we get v times exponential of u over v. Integrate from v minus v to v of dv. This we get from integration from 1 to 2 v times e minus e to the -1. Okay. And then what do you get? So you get e minus e to the -1 over 2 times. You only have one v to integrate, so you get v squared over 2 from 1 to 2. And then if you compute this, this is 3 over 4 times e minus e minus. Okay. Yeah. Okay. Okay. Yeah. Okay, maybe there are one or two more exercises you can try. I will provide solution. So before we end this multiple integral, right? Do you have any questions you want to ask? Concept question or example questions from examples? Question? Yeah. For multiple integral. Okay. Let's do it. Okay. So what did we do in multiple integral? Okay. So what did we do in first thing we do? Okay, what's the first thing we do in multiple integral? So we define the double integral using doubly limit and doubly sum. Okay. So we use doubly limit and doubly sum. Sum of what? What are we summing actually? What are we summing? So maybe I put I equals 0, j equals 0. Fx I star yi star times delta I. Okay, so we use rectangle to approximate the volume, okay, of this double integral. So why we taking to infinity? Because we make the rectangle smaller, 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 smaller until you reach a limit to a line. Okay, so when up the volume. But when does this double integral define the volume? Okay, when does it define volume? When does this define volume? Only when my surface is always positive. Okay, when it is always positive, then the integral, the double integral will represent the volume under the surface. Okay, volume of the surface or under the surface. The surface F. Okay. Remember that we have one example where we compute the function, the multiple integral function to be 0, but the function is non-zero. Right or not? Remember? You still remember the example? We compute the double integral to be 0, but the function is non-zero. Okay, so that means that in some part is positive, some part is negative, they cancel out. Okay. So when you want to get a volume, you need to make sure your surface is always positive on the domain. Okay, this is the key part. What else? And then we go, I think we go to polar coordinates. Okay. Before going to polar coordinates, there are some properties of double integral. Or actually, you can extend it to triple integral and so on. So in this case here, we just call it multiple integral. Okay. So these properties are actually linearity. Okay, linearity. So you can take the constant now and do the integral, or you can split the integral into sum of function. You also can split the integral into disjoint union of domain. Okay. Right? Okay, so these are the property you can do. Disjoint union. Okay. So disjoint union means okay, let me just write out what I'm trying to say here. So okay, so what's disjoint union? So if I have my domain split out into two parts, okay, what can I do is I can also split my integral into two parts, and then I just add them up. You don't even need to be disjoint, okay? They just need to, they can be intercept on boundary, okay? No need to disjoint. If disjoint meaning if an element is in one set, it's not in the other set. This is called disjoint. But we allow intersection on the boundary. Okay, we don't allow intersection. So something that we don't allow is something like this. Okay, there's something non-empty here. So this is not empty. So this is a not allowed scenario. Okay, So what is allowed here is you can intersect along boundary here like this. Okay, intersect along boundary. The disjoint union, I mean this. So let me move this to here. So this is 1, this is 2, this is 3. So this is disjoint union. The first one is disjoint union. Okay. The second one is intersect between on the boundary. Third is there's non-empty intersection. If it is not empty, then you cannot do it. Can understand or not? Uh-huh. Yeah. Yeah. We are talking about where the f is continuous, then we integrate over there. Yeah. This is the pre-assumption. And this is a pre-assumption. We have continuous function over this domain, and then we try to integrate. Yeah. Even if it is not continuous on the boundary, right? As long as it is finite number of curves, then it is integrable. It's still integrable. This is our theorem last time. Okay. Even though it is not integrable on this line here, because this is finitely many, just one in particular, then it is integrable. Okay, as long as f is bounded also, must be bounded and discontinuous on finitely many curve, then f is integrable. Okay, yeah. So these are the nice property linearities. So you can see that last time I mentioned, so you go from a set operation into number operation. Okay, union become class. Okay, so this is something to observe here. Okay, this happen quite frequently in mathematics across area. A set union become a class in a number. Okay. Okay. So next we learn next is about change of variable. Okay, change of variable. So how many type of change of variable we learn? Okay, before that, we learn integration over general region. Okay. So what's the key idea here? Okay, what's the key idea here? So first, you need to know how to build your domain or domain space, okay, using cross sections. Okay, you need to know how to split your domains into lines, into curve, okay, and then build them together. Find your domain. Okay. Second, you need to care about your integration order. Okay, you need to make the right integration order. So integration order controlled by what? Okay, first thing, it is controlled by Fubini's. What's Fubini's theorem? If f is continuous on a rectangle, or higher dimensional case is a cuboid, okay, then the integration domain doesn't matter, right? You can change dx, dy, dz, or dz, dy, dx, everything you can do, okay? The integration order doesn't matter, okay? So where does it matter? It matters when you want to compute the actual function. Sometimes one order is harder to compute than the other order. Okay, there's an example that if you integrate over one variable, you need to do integration by part, but over the other, you don't need to do it first. But since you already do the other part, then you already reduce it to one variable case. Okay, so it will become easier. Okay, so this Fubini's theorems help you to compute the easier integral first. Okay, make sense? Okay, so
yeah, integration order, and then this will be need. Second is depend on what kind of controlling you have on your variable. Okay, so you need to place it nicely. So for example, if your x, okay, so let's say, so for example, second is for example, okay, example. So example, if your y is controlled by some value ab, but your x is controlled by some function of y. Okay, so which one do you want to integrate first? Which one do you want to integrate first? Dx first or dy first? Okay, we want to do dx first because why? Because x is depending on y. Okay. After you integrate over x, then you integrate over y. You add all everything on y direction. Okay, yeah. So this is depending on how you control your domain. Okay, this also generalized to three-dimensional case. Okay, x, y, z. So does x depend on y and z or not? Does y depend on x and z or not? Okay, so you slowly close down. So when you do this closing down, right, it is actually building your domain using cross-section area. Okay, so along each y, what happened to your x? So along each y, what happened to your x? Make sense? Okay, along each y, what happened to your x? Okay. Okay, so next is change of coordinate. Okay, so we go to different spaces, depend on what domain we want. Okay, depending on the domain shape. Okay, so sometimes, okay, in two variable case, how many coordinate we have? Okay, we have regular, rectangular coordinate. Okay, and polar coordinate. Okay, so we have two of them, rectangular and polar. Three variable case, how many coordinate we have learned? Okay, we have learned rectangular, cylindrical, and spherical. Okay, so what are these variable change? Okay, in rectangular we have x, y, z. Sorry, x, y in two variable case, but x, y, z in three variable case. Okay, so how you go in between polar coordinate and rectangular coordinate? So here we have r theta, and the way to go between them is x equals to r cos theta and y equals to r sin theta. Okay, so the function in xy becomes a function in r cos theta and r sin theta. Okay, so what's the range? Okay, of course we also need to talk about the range of x and y. Okay, so in the R2 case, we consider everything. Okay, how about in polar coordinate case? Our radius is all the positive radius. How about angle? Angle is a whole circle, 0 to 2 pi. Okay, but how does the integral change in this case here? Okay, how does the integral change? How does the integral change? You see, the domain don't change, but the way to describe the domain change in terms of r theta. So what happened to my function here? Okay, my function, the variable also changed. At the same time, we introduce a Jacobian. Okay, we introduce Jacobian, which is dr, which is r. So r dr d theta in this case. Okay, so this is the change of variable for polar coordinate. Okay. Similarly, we have higher dimensional case. So we have higher dimensional case. So in cylindrical coordinate, we have what? R, theta, and Z. Okay. Spherical, what do we have? R, theta, and phi. R, theta, and phi. Okay. So how to go between rectangular, cylindrical, and spherical? Okay. So we just tell you how to go from rectangular to the rest. Okay. So how to go from rectangular to cylindrical? X equals to r cos theta, y equals to r sine theta, z remain as z. Okay. How to go from rectangular to spherical? Let's me in this case we move it here, maybe more convenient. So let's move it to this side. Okay, move it to this side, more convenient. So what is the, I think this is harder because this is long, very long, longer. So what's the long formula here? R, okay. I think in the note it's called rho. So let's put rho here. Rho sine phi cos theta. S equals to rho sine phi sine theta. And then, sorry, this is y. And then Z equals to rho cos phi. Okay, hopefully I'm correct. Okay, so how about the range? How about range? What happened to the range? What kind of angle you need to consider in each case here? Okay, so we need to able to cover all the R3. So you need to consider all the X, Y, Z. And you need to consider all the X, Y, Z from negative infinity to positive infinity. But in the cylindrical case, what do we need to consider for radius? We only need to consider from 0 to infinity. How about angle? Angle is 0 to 2 pi. But these two only manage to cover a single R2. So how to cover the rest? You just take all the height. Okay, so you take from negative infinity to infinity. Okay, so how about spherical? Okay, how about spherical? So what are these numbers representing? So rho represents the radius of your sphere. What is theta? Theta represents the angle from the positive x-axis. How about phi? Phi represents the angle from the positive z-axis. So how do you cover the whole R3 using this angle? Okay, so radius. Similarly, you need to be able to extend to everything. How about theta? Theta you can take 0 to 2 pi. Okay, so once you have this, what's left? What's left? Yeah, what's left? Yeah, what's left is phi. So phi is going from where to where? Negative pi to pi. You can take negative pi over 2 to pi over 2. Let me think where is it. Okay, wait. So let me think where is negative pi. So it's here. Yeah, you can take this. Okay, you can take this, but the convention is take. Okay, wait. Let me think again what you are trying to say. So our angle is going from positive the axis here. So here to here is 0 to pi. So where is pi to negative 2 pi? So you say pi over 2 to negative pi over 2. So let me think. Yeah, it's still, wait, let me think. Yeah, it's still this side here. Okay. So our convention is to take 0 to pi. Okay, you can change to minus pi over 2 to pi over 2 as well. Is it? Wait. Let me think. Wait. Let me think. Wait, I'm wrong. You know why am I wrong? Because if you take from minus pi to pi over 2, okay, the only way, what we take, okay, actually depend on what I decide on the first two first. Okay, what I decide on the first two is I take all the radius, okay, and then I take 0 to 2 pi, so going horizontally. But you just fill in the top part. You never fill the bottom part. You never fill the part below z equals 0. Wait. Let me finish this question first. Yeah. Why the pi over 2 lies on this x-axis? Okay, so this is the z-x. Okay, yeah, correct. Okay. So what's the question? So why the pi over 2 lies on the x-axis? Is it? Phi is calculated from positive z-axis. So if you go from 0 to 2, minus pi over 2 is here. From positive z-axis. Okay. Okay. So if you're gonna take pi to minus pi over 2, what you only get is half of R3. Can you see why? Can you see why? You cover all, but you cover too many. Because I already covered from 0 to 2 pi horizontally. I mean in the R2 plane. You just build extra space. You build extra space. Many. Your question is like, the question is like this. So you see, the question is similar to this question here. This question is a higher dimensional analog of this question. So this parametric curve is, I hope you still remember, cos t sine t. Okay. So to draw this circle here, I just need t to from 0 to 2 pi. If I go beyond 2 pi, what happened? I still stay inside the circle, but I go more than one round. You get what I mean? So for example, if I go from 0 to 4 pi, so I already moved two times the circle. Is this English okay or not? Times the circle. For t, for this domain, RT represent times the circle, represent the curve going, all right, represent the curve going around the circle 2 times. Okay. So I mean, if you take more, you will produce. You still get the same space, but you don't get a one-to-one map. You don't get a one-to-one map. If you talk about position, it's like the cosine sine function, right? You can periodically get back the same answer. Yeah, that's the problem. But we don't want we don't want it to happen because we want it to be one-to-one map. Yeah, we want to have injective. We want to have one-to-one map. Yeah, this is the problem. Because this is the Jacobian. This is the Jacobian. This is the next part. This is the Jacobian theorem, right? I don't know what's the name, but let's call it Jacobian theorem. So if TUV equals to XV SY, okay, is a one-to-one map. Okay, one-to-one map. So we can really change our function. Okay, we can change our function into a new integral that is happening in UV. Okay, XUV, YUV. At the expense of what? We need to introduce the Jacobian of new D. I call it A prime. Okay. Yeah. Okay. So you need one-to-one. Okay, need one-to-one here. You really need one-to-one to be able to change variable for your integral. Okay. Make sense? Okay. 之前what do you want to say? Later, okay. Okay. Yeah. So you can realize that actually this is not unique. It's not unique. It's not unique here. So this range here is not unique. Okay. As long as you can produce a one-to-one map, it is possible. Okay. For example, I don't want to take 0 to pi, also can. I take what do I take? I take the other side, also similar. It's similar. Okay. Or you can't see what I say. Okay. For example, right? Let's say just now you want to take the whole range here. Okay, you want to take the whole range. If you take the whole range here, you don't need to take theta from 0 to 2 pi. Can you see why? To build a one-to-one map. You just need to take theta from 0 to pi is enough. Okay, so okay, this is a bit extra. So here is extra here. Okay, so let's say you want to take theta from 0, phi from 0 to 2 pi. Okay, you have 0 to 2 pi in the, what's the direction? The zx direction. Okay, and then of course you still need radius to infinity because you want to extend this circle to infinity. But how about the other direction, theta? What you can, to build a one-to-one map, you can take theta from 0 to pi is enough. Does it make sense? So you just rotate 0 to pi, then you will get everything. I think so. Yeah. You can think about it. True? Yeah. This is my claim. Yeah, check if it's true. I think it's true. Okay? Yeah, I mean, it's not unique, but you need to make sure you have a one-to-one map. Very important. Because otherwise, right, you integrate too many stuff later. But I mean, yeah. Okay. Yeah. So I haven't finished yet. So how to change in between these two? Yeah, these three. So let's start with this XYZ of dx, dy, dz. And how to go between these two? So the Jacobian you have for spherical is r squared sine phi. Okay, dr d theta d phi. Okay, you still integrate over the same domain, but for cylindrical, what's the Jacobian? You only get r. So this Jacobian here is really similar to the polar coordinate, and this is no coincidence here, because you only change variable for x and y. Okay, you only change variable for x and y. So there's no coincidence here why they are the same. Okay, it's not a coincidence, it's exactly because you only change variable for the xy plane. Okay, but there's some advantage between this different advantage of using this polar coordinate, this spherical, cylindrical, rectangle, based on what domain you want to integrate over. Okay, so for example, for rectangular, right, it is very good if you want to integrate over rectangular stuff. Okay, for cylindrical, you get something. If you see something cylindrical, you might want to use cylindrical. If you see cylinder, you might want to use cylindrical coordinate. Okay, or sometimes last time we got see a cone example, right? Or a cone. Okay, spherical. If you have a sphere, okay, or something like this cut off. Okay, yeah. Any question? How about polar? Polar, if in polar you might want to have circle, okay, or some polar rectangle, also can. Okay, compared to the actual rectangle. Okay, so you should observe what integration domain you get, and then decide which coordinate you want to use. Right? Because in one of the coordinate, maybe all the integration domain become just constant. Okay, you just need constant to describe them. But in some of them you need to use variable. Okay, so constant is easier, right? You just plug number in and then get it. If it is function, then you need to integrate again and again and again. Sometimes the function could be hard, like square root of something. Okay. Typically, when you see square root, right, you might want to guess if there's some circle inside there. Usually, not always true, but usually. Square root of something square. A question? Question? Yeah. I mean, we finished already, right? Okay, so okay, then next week we'll continue with vector function and then vector calculus. Okay, and then we will end at that topic. Finish the semester. Okay. Huh? What do you mean? Cancel? Why? I mean, finish the lectures.